Now we're going to start our final unit, which is over probability theory. So probability theory is a really deep topic that has a ton of applications. The bad news is that we're only going to be able to get into the basics of probability theory, so we're only really going to be able to scratch the surface. The good news, though, is that as a result of that, this section I think will feel a lot less technical than our previous section. So this might feel like a breath of fresh air as we come to a close for this class, just because I'm hoping that this stuff, if it's not already familiar to you, will at least feel relatively accessible. So this is not going to be nearly as technical as our last section, but it is probably more important in practice just because probability theory is applied everywhere. So let's look at some of the basics for probability theory. Here we're going to define some basic terms that we need. In probability theory, you're always talking about a sample space, which is the space of all possible outcomes for whatever experiment you're talking about. So for example, if I was flipping a coin, the sample space would be heads and tails. Those are all possible outcomes, but that doesn't mean that I'm going to get both heads and tails on my next coin flip. I'm just enumerating all of the possible outcomes, and probabilistically one of them is going to occur. And an event is an outcome or a set of outcomes that you might expect from a random experiment. So for example, I could talk about the event that I flip a heads. So that would be just a subset of my sample space. I want to know the event that I flip a heads when it's possible to get either a heads or a tails. And here we have this basic probability principle that says that if all of the outcomes that you're describing are equally likely, then it's easy to compute the probability of a certain event occurring in a single instance of your experiment. You just need to take the number of outcomes in the event and then divide by the total number of possible outcomes. So you would take the number of outcomes in E, your event, divided by the number of outcomes in your sample space. And so for the example that I've been talking about, if you wanted the number of outcomes that you're happy with, if you want to flip heads, divided by the number of outcomes in your sample space, then that would just be 1 over 2, and clearly that agrees with your intuition that you should have a 50-50 shot of flipping a heads whenever you flip a coin. And notice that just from this formula, we immediately get these two corollaries, that the probability of each outcome has to be a number between 0 and 1. So probabilities will always be a number between 0 and 1. It's okay if you want to convert those to percentages. So if you want to measure a probability as between 0% and 100%, that's also fine. And you also get that the sum of the probabilities of all possible outcomes is 1. In other words, the probability of flipping a heads plus the probability of flipping a tails, those need to add up to 1 because the sample space is a guaranteed event. In other words, you have to flip at least either a heads or a tails. Those are the only possible outcomes. So the total probability that either a heads or a tails occurs would have to be 1. So first, let's focus on writing down the sample space for some of these experiments. So remember, the sample space is the set of all possible outcomes. You can write it in set notation like this. So you would use these curly braces. Let's say that you're flipping 2 coins. I'm going to use the first letter for the result of the first coin, and then the second letter will describe the second coin. So you could flip a heads and then a heads tails, a tails heads, or a tails tails. And those are all possible outcomes in that case. Similarly, if you roll a die, I'm assuming this is just an ordinary 6-sided die, so this would be 1, 2, 3, 4, 5, 6. Notice that this would be the sample space for a fair die, where each side has an equally likely chance of coming up, but it's also the sample space for something like a weighted die. So if someone is cheating and using weighted dice, then this is still their sample space. So the sample space does not include the probability of each of these things occurring, but what we know is that if your experiment is fair in the sense that all outcomes are equally likely, like up here, then you can use this probability principle that we were using up above, where you can just enumerate the number of outcomes that you're happy with, or the number of outcomes in your event, and then divide by the total number of possible outcomes, and that will tell you the probability of that event occurring. So the sample space is sort of agnostic to the probabilities of each of these things occurring, but if all of these events are equally likely, then it's easy to compute the probability of a given event. And then in C, we want to toss a coin and roll a die. So I want to introduce something that's sort of nice whenever you're organizing a sample space. So you may notice that whenever you had 2 coins that were being tossed, we had 4 possibilities in total in our sample space, which is 2 possibilities for the first coin times 2 possibilities for the second coin. Similarly, here we have 2 possible outcomes for our first experiment, where we toss a coin, and 6 possible outcomes for our second experiment, where we roll a die. And therefore, we're going to have 12 outcomes in our sample space altogether. So it'll be 2 times 6. And one way of seeing that is to organize the sample space as a table. So maybe for the result of the coin toss, I will just write heads or tails as those possible results. And then similarly, for the result of the die roll, I can just enumerate all of the outcomes up here. And now the interior of this table will represent my sample space. So I could get a heads and then a 1, a heads and then a 2, and so on. And if I just write down all of these possibilities, these will be all of the possible outcomes that I could have for this experiment. And you'll notice that there are 12 of these in total. So the sample space here could again be written as a set. So if you wanted to, you could enumerate these as heads 1, heads 2, and so on. But in this case, because this experiment is built up of 2 independent sub-experiments, it's easier to just organize the sample space in the form of a table, and then these 12 events, or these 12 outcomes, are your sample space. So I would probably write the sample space in the form of a table, and then the sample space itself is the interior of this table. Notice that we could have done that for part A here. So I could write the result of the first coin toss, and similarly the result of the second coin toss here, and then the interior of this table will just enumerate all of the possible outcomes. So heads, 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 tails, tails, heads, tails, tails. So if you want to write your sample spaces in the form of a table whenever you have 2 independent events going on, then that's totally fine with me. But it's also okay to just use the set notation where you enumerate them all on one line. So next, let's look at example 2 here. So here a fair die is being rolled, and we want to find the probabilities of these given events. So in part A, we want the probability of getting a number greater than 4. So if you want the probability of a particular event, what you should do is you should enumerate all of the elements in that event, or all of the outcomes in that event. So here we have a number greater than 4. If you're rolling a die, that would mean that you're looking at the event 5, 6. So remember, an event is a set of outcomes. It's not a probability. So this is the event, but what we want is the probability of that event. And the probability of that event is going to be the number of elements in that event, so the number of elements in 5, 6, which is clearly 2, divided by the number of elements in your sample space. Now we've already seen that the sample space for a die is just 1 through 6, so there's 6 elements in the sample space, so this would be 2 out of 6, which is 1/3. And again, if you want to convert this to a percentage, you could, so this would be a 33.3, sorry about this, there we go, 33.3%, that would also be fine. I'm normally just going to leave my probabilities as some number between 0 and 1. But if you prefer the percentage, then that's totally fine. Similarly, if you want to know the probability of getting a 2 or a 5, then you would list the outcomes that you're happy with. So my event in this case is 2 or 5. Those are the 2 outcomes we're happy with. And again, the probability of this event is going to be 2 out of 6, because there are 2 elements in that event, and there are 6 elements in my sample space in total. And for these, I don't even care if you want to reduce the fractions. We'll see some examples later where it's actually preferable that you don't reduce, because we'll need to be adding fractions, and in that case it's preferable that you keep the original denominators just so that the denominators match. But I'll talk about that in a bit. So next let's look at example 3. It says 2 dice are rolled, find the probabilities of rolling the given sums. So the number that's being described here is not the number on a single die, it's the sum that you get if you add these together. So it's like we're playing Monopoly and we add together the 2 dice that we roll. So here I've just given you the sample space. So I'm thinking of the x coordinate as telling me what the result of the first die is, and then the y coordinate is telling me the result of the second die. So this is our sample space for rolling 2 dice. And now what we can do is we can look at this sample space. Notice that the sample space itself is this interior for the table. So there are 36 elements in total because this is a 6 by 6 table. So the sample space has size 36. And we want the probabilities of rolling these given sums. So in this first case, in part A, the event that we're describing is the event that we roll a 2. Now, in terms of our sample space, that would just correspond to this element, or this outcome, because the only way to roll a sum of 2 is to roll snake eyes. So if I were to write this event in set notation, it would look like this. It's that event that has a single ordered pair. So the probability of E would just be the number of elements in E, which is 1, divided by the number of elements in your sample space, which is 1 out of 36. And I'm not going to convert that to a percentage. I don't really care what the percentage is. I just want to leave it as this fraction. Similarly, if we want the probability of rolling an 11 or more, we could write the event that we're interested in. The event that we're interested in is rolling an 11 or more in total. That corresponds to this bottom right corner. So you could roll a 6-5, a 5-6, or a 6-6. There is something that might be worth pointing out about these totals. The sum on a set of dice is constant on these diagonals. So notice that if I look at this diagonal, the sum here is 11. Similarly, for this diagonal, the sum is 10. And you'll notice that the most popular diagonal here is a sum of 7. So the longest diagonal has a sum of 7. And that's important whenever you start talking about the probabilities of rolling certain numbers. So let's say, again, you're playing Monopoly, and you want to know what the most likely thing is that you'll roll if you're rolling 2 dice and totaling them up. Here it's clear that getting a sum of 7 is the most likely outcome relative to all of these other outcomes. So I don't mean that you have more than a 50% chance of getting a 7. I just mean that 7 is the likeliest of all of the possible totals. And so notice that you have a 6 in 36 chance of rolling a 7, whereas you only have something like a 1 in 36 chance of getting a total of 12. So that's why if you play Monopoly, you'll get some of these middling numbers a lot more than you'll get these extreme values like rolling a 2 or rolling a 12. Okay, so the event that we're interested in, we can again just write down the event as a set. So we're looking at 6-5, 5-6, and 6-6. This event has 3 elements in it. So here the probability of this event would be 3 out of the 36 possible total outcomes. And if you want to reduce, you can. That would be 1/12. So these next few examples are just applying similar strategies. I think actually I will go ahead and finish out these examples in this video, but I'll go a little bit more quickly through them because I suspect you're probably getting the idea. So if we want the probability of landing, whoops, sorry, that got covered up. If you want the probability of landing on a multiple of 3 in this spinner, so we have to first look at all of the outcomes that we're happy with. In this case, we're happy with a 3 or a 6 because we're looking at the multiples of 3. So we're happy with 2 out of the 8 outcomes. So the probability of the event that we're talking about would be 2 out of 8, which would reduce to 1/4 or 25%. So there's a 25% chance that you get a multiple of 3 here. Similarly, in 5, if you have a bag of 20 cherries, 14 of the cherries are sweet and 6 are sour. We pick a cherry at random. What's the probability that it will be sweet? If you want the probability of that particular event, you enumerate all of the elements that live in that event and then divide by the total number of outcomes. So I'm thinking of an outcome as a particular cherry that I'm picking out of the bag. So there are 20 possible in total, but I'm only happy with 14 of those outcomes. So the number of outcomes that I'm happy with would be 14 divided by the total number of outcomes, which would reduce to a 0.7 or a 70% if you like. So any of these answers would be fine. Similarly in 6, suppose you pick a card out of a standard deck of 52 cards. What's the probability that you will choose any given card? Like, what's the probability that you choose the ace of spades? And the point is that the probability of drawing your particular card of choice would be one option out of the 52 possible outcomes that you would get from drawing a card. So this would be 1 out of 52. In 7, suppose you pick a card out of a standard deck of 52 cards. What's the probability that you will choose a spade? So notice that there are still 52 possible outcomes, but this time we're happy with more than one outcome. So we're happy with any of the spades. There are 13 spades in total. So there are 52 cards in a standard deck. There are 4 suits. The spade is one of them. That means there's 13 cards of each suit. So we'll have that the probability of this particular event will be 13 out of 52, which would reduce to 1/4. Or if you like, 0.25, or again, if you'd like 25%. Any of those are fine. And then lastly, in 8, a group of people were asked if they had run a red light in the last year. 423 responded yes, and 211 responded no. Estimate the probability that if a person is chosen at random, they've run a red light in the last year. So here we want the probability that they've run a red light. So I need the number of outcomes that we are interested in divided by the total number of possible outcomes. So I'm thinking of this survey as being my total number of possible outcomes. So I'm imagining that this survey is representative of the population at large, and we're just using this to sort of estimate the baseline probability that someone has run a red light in the last year. So we know that 423 people responded yes, so that will be the number of outcomes that we would be interested in. But notice that our denominator here is not going to be something like 211. What we're interested in is the total number of possible outcomes. And for that, we would need to sum the yes and no responses. So if I add those together, then what I would get is 634. And that will give me my denominator. Because again, to compute these probabilities, assuming that each of these people are chosen uniformly at random, we would have 423 outcomes that we're happy with, and then 634 outcomes in total between the 423 yeses and 211 nos. And for things like this one, I probably wouldn't worry about trying to simplify it or anything. I would just leave it like that.